Hi, am I audible? Okay, thank you. So let me bring out my cane. Yeah, so my screen is visible now. Okay. Okay, so myself Subrata Samanta. So I am your teaching assistant for the thermal physics course taken by Professor Demalla Banerjee this semester at NPTEL. So, so I am a first year PhD student in the Department of Physics at IIT Kanpur, and my research is based on the theoretical aspect of high energy physics. Okay. So the Ministry of Human Research Development, Government of India financially supports my research under the Prime Minister Research Fellowship scheme. Okay. So today I will going to discuss mainly the assignment 2 and assignment 3 problems. Okay, and before I going into this, okay, I will like to discuss some basics about week 2 contents as well as week 3 contents, and then do the assignment 3 problems. Okay, so if you have any questions from the week 2 and 3 contents lecture, so the questions raised in the discussion forum, I already sum up answer some of these questions, but okay, so let me check. Okay. Yeah, I think some of the problems remained unanswered. Okay, the assignment problems at everything index. Okay, so go through the systematically one by ones. Okay, so first we start today. Yeah. Okay, so today I will going to discuss first briefly about solid angle, and then I will go through the effusion process, effusion, and let's say the mean free path. Okay. Then I will go into the transport phenomena process, transport properties of gases, and discuss the problems in the assignments in betweens. Okay, so so first we discuss about briefly about the solid angles. Okay, so let's consider let's consider a circle. Let's consider a circle. Okay, and let's consider a circle of radius, let's say r. Okay, so we are interested in a region, some portions of this circle, let's say this. So these portions of the circles we are interested. Okay, so these portions makes an angle theta at center, let's say O. So this arc length, can you tell me what is the arc length for this case? Is equals to, is the radius is r and the angle is theta at the center, so what is the values of s? Yeah, so at theta, right? So this implies that theta actually is by r. Okay, so s is the arc length, these portions we are interested. So now I can ask that what is the angle, okay, subtended by the whole circle at its center, right? So then how to do that? Then the whole circle means that the perimeter of the circle. So s in that case s is 2 pi r, right? So in this case theta actually 2 pi r the whole portions of the circle, the whole perimeter of the circles, okay, is 2 pi r is 2 pi. So the whole circle makes an angle 2 pi at its center, right? So similarly, I extended this idea to sphere. Okay. So in case of sphere, let's draw a. So let's draw a some portion of the sphere. Okay. So let's draw some portions of the sphere. Let's say choose. So we are interested this region, this smallest region. So this region, this is, let's say this is x-axis, y-axis, z-axis. Okay, and this region makes an angle theta at the origin. This is O. Okay. So this portion makes an angle, let's say this is the differential angle. Okay, let's say this call is the d omega, and this area portions, okay, is called dA. So now we are in 3D. So the length element is converted to the area elements. Okay, so it's dA. So so this, let's say the radius is r. Okay, and this angle is theta. Okay, and let's say this point, okay, any point about, we have extended this point, so this r, this theta. Okay, so let's say this point. So in this case, this is your phi. So can you tell me what is the area element? This is the smallest part of the sphere. Okay, we will calculate. So for this case, so this is a r, right? So let's say this point, so this point, so this is r and this is theta. So what is this element? Just as previous, right? So r d theta, this is d theta. Okay, and this is r, this is r d theta. Now this, okay, so this case, first we calculate this length. Okay, so what is this length? This r theta. So this is r sin theta, and then you shifted a small angle in the phi direction. Okay, d phi. So this is your d theta. In this direction we have shifted d theta, and in this direction we have shifted d phi. Okay, so then this element is r sin theta into d phi, right? R sin theta into d phi in the phi plane. Okay, in the phi directions, r sin theta, and then we are shifting is d phi. So r sin theta d phi is total this. So that means it's r square sin theta d theta d phi, right? It's clear? Hello. Okay, so then we similarly calculate, let's say d omega. So this d a by r square, right? So this d omega actually the solid angle elements. Okay, the small portions of dA. Okay, the similarly as in the circle case. Okay, the small portions of x makes an angle theta at the origin. Okay, and similarly the small portions of the surface element of the sphere makes an angle d omega at the origins. Okay, because we are now in 3D. Okay, so then this actually sin theta d theta d phi. Now I can ask that what is the angle subtended by the whole sphere at its center, right? So similarly we integrate over the about the whole theta range and phi range. Okay, so then the omega just integrate our what is the theta range in the spherical coordinates. It's 0 to pi, right? So 0 to pi sine theta d theta, 0 to 2 pi, the phi range is 2 pi. That is cover the whole sphere at a constant radius, right? So then we get this value is 2 and 2 pi, so it's 4 pi, right? So that means the sphere makes an angle 4 pi at its center. Okay, that is called the solid angle, total solid angle of the sphere. Okay, so someone asked the questions in the discussion forums. Yeah, so I think some Obi Sharma. Okay, so this how the 4 pi get. Okay, how we get the 4 pi for this case. So now it's clear, right? Okay, so then we go through into the effusion process. Okay, so from this, okay, so let's say start with this diagram. Okay, so let's consider this portion again. So we are choosing this particular direction. Okay, and let's say makes an angle, so this is a sphere. So this is a sphere, so we choose these portions. Sphere, we choose this portion, right? So this is a small strip. Okay, and let's say this point, this is a R, and this point, so this is a theta, right? And this is a d theta. So this is your d theta and this is theta, right? And we are integrate over the phi. Okay, so this is a, we can make a strip on in the phi x, in the phi directions. Okay, and we are interested, this is a particular direction. Okay, we choose particular direction, we choose. Okay, and we make a strip around this particular directions. Okay, so this is your, let's say, z axis, and we can strip, we can make a strip on this particular direction. Okay, so then again we calculate the d omega. So in this case d omega is so we are integrating over the phi, so it's sine theta d theta, and we can integrate over the phi, 0 to 2 pi. This is actually 2 pi sine theta d theta, right? So this strip makes an angle 2 pi sine theta d theta at center. Okay, so this is a solid angle for this line element, this strip. Okay, whole strip makes an solid angle 2 pi sine theta d theta at center, right? So now, so then I can ask that how much fractions of the molecule now go into the Maxwell-Boltzmann distributions. Okay, so you know that the from Maxwell-Boltzmann distributions, okay, so how much the fractions of the molecules. Okay, so let's say the number of molecules, the Maxwell-Boltzmann MB distributions, so tells that the number of molecules. Okay, so number of molecules per unit volume, with velocity, let's say v2 v plus dv, right? This is actually n fv dv, right? This is right? Per unit volume. Hello, it is clear? Yeah. So now I can ask that the number of molecules. Okay. Now I can ask that the number of molecules per unit volume, per unit volume with angle theta to theta plus d theta and velocity or speed, not a velocity, speed is the right language to say, speed is v2 v plus dv, right? So the distributions then in is modified in fv dv into 2 pi or okay, so then how do I know, right? So this is a fractions of molecules, right? So then we can divide it by 4 pi, because the total sphere, let's consider a particular molecules, okay, and we make a sphere around it, right? So the whole sphere makes an angle, solid angle is 4 pi, right? So the particle can randomly move any directions, right? So we can consider a sphere, that means the particle move any of this portion of the sphere, they can move. So we can consider the whole 4 pi direction, 4 pi, right? Now we are interested in some portions, right? So that's why we divided by 4 pi, the proper normalizations, okay? So n fv dv 2 pi sin theta d theta, right? So then this is get half in fv dv into sin theta d theta. So it's clear why we divided by 4 pi. So we divided by 4 pi because it's a proper normalization. Okay, we are calculating the fractions of molecules are per unit volumes with an angle theta to theta plus d theta and the speed v to v plus dv. Okay, but the total is 4 pi, right? So that's the proper normalization. So we divided by 4 pi. So this is that is we gets now. So then we calculate that. So it's clear now. So now we are going to, so this is an important formula we are using repeatedly, okay, in the later part of this class. So now we are interested in something else. So now we are going to discuss that what is this particular directions, right? So we choose a particular direction, right, and makes an strip from on this particular directions around, okay? So now we are going to discuss what is the particular direction. Let's say consider a oil, okay, it's a oil, okay, and molecules are heat into the walls, okay. So that is your particular direction. So molecules are heat into the walls. We calculate the pressure, right? That is the from this diagram, okay. So we calculate the pressure. So then let's consider a so this is your area vector from this wall, okay, n cap, and this area actually dA, okay. This is a small portions of this wall, okay, or let's say A, the area is A, the total area is A, and this is the n cap, and molecules are hitting to the wall, let's say at an angle theta, okay. So v velocity and let's say in dt time, okay. So molecules are hit to the walls at an angle theta with the normal, right? So similarly this is v dt and okay, just a minute. So Yeah, so then we can calculate that what is the volume covered by this these small portions. So here we calculate that the number of molecules per unit volume with angle theta to theta plus d theta, speed v2 plus dv, right? So in this case the same thing, speed is v2 v plus dv, and per unit, so here we calculate per unit volume, but here is a definite volumes, right? So we first calculate the volume that cover in this small portions, small time dt, okay, and then yeah, so small time dt, right? So then so first we project this v dt cos theta. So this is a v dt and this is a theta. So we are calculating the normal. So the projections of v dt into the normal direction is v dt cos theta, right, into this area, right? So a, this is the total volume v in time dt, in time dt, this is the total the volume, let's say dv, it's v dt, so e v dt cos theta. So in time dt they cover these volumes, okay. Yeah, so this is the normal direction. So we are actually calculating the normal to the walls, right? So that's why they are projecting this v dt into the normal directions, v dt cos theta, right? So similarly then the number of molecules, so because we are here with the particular directions, this is a normal, right? So in this case if the molecules are hitting to the angle theta with the normal, so we are projecting this with the normal, right? So then we can apply this formula, the above formula, right? So then the number of molecules hitting a wall of area A, number of molecules hitting a wall of area A is yeah, so area H half in v, so in this case v dv sin theta cos theta d theta, sorry there is a fv also there, so f of v dv, right, half in v f of v dv sin theta cos theta d theta and area A. So this is the total, right? So with v2 v plus dv, velocity v2 v plus dv, and angle theta to theta plus d theta. So in this case there is no unit volume, okay, so it's some volume dv elements. So then yeah, so from this point if you see that the velocity distribution is not f of v, it's v f of v, right? So let's say we consider a box. In the previous lecture class I already told that if there is a hole, right, so that you can I want to calculate the distributions of the particles the passing through this hole, right? So this is not a Maxwellian distribution, right? So it's some kind of looks like this, okay. So then is the v dv, the velocity distribution is v f of v, right? So now if you know that the v and f of v is v square e to the power minus alpha v square, right? So this is a v cube e to the power minus alpha v square, okay. So if you want to calculate the distributions of the molecules that passing through this hole, okay, it's a v cube e to the power minus alpha v square, not the Maxwellian distributions, okay. So it's now clear, it is clear now, right? Okay, yeah. So now we calculate from this the okay, so from this formula we derive the ideal gas law, okay. So how to derive the ideal gas law from this formula? So this is your main formula, okay, so we can mark this. So now what is the pressure? So we want to calculate the pressure, right? So the pressure that the molecules gives to the walls. Okay, so the pressure actually is definition by the force per area, right? So what kind of force and what kind of area? So area is the contact area and force is the perpendicular contact force, right? So in the wall, so the perpendicular contact force, okay, so let's say written that explicitly, that's the perpendicular contact force, the force to the wall, okay, this is the contact force, by divided by contact area, right? Yeah, so perpendicular contact force by contact area. So if a molecules moves in momentum mv, right? So there is a well, yeah, so there is a wall and the molecules are hitting perpendicular to the surface. uh, the momentum is pmv, right? So if the molecules not perpendicular, if the molecules hitting to the angle theta, so then and moving with the velocity v, right? So the momentum is p equals to mp, right? Now I am already defined that the perpendicular contact force, right? So the portion is that perpendicular, this is mv cos theta, okay? So cos theta components, right? So and then they back to again the same momentum due to momentum conservations, okay, minus mv cos theta, right? So the hitting to the momentum is mv cos theta because they are hitting to the walls, let's say at an angle theta with the normal, right? We are calculating that the perpendicular components, that's why mv cos theta, and the reflecting back with again the same thing, minus mv cos theta, okay, due to the momentum conservations there are no loss in the wall. So the total change in momentum, that is called the impulse, okay, it's 2 mv cos theta, right? So if we multiply this 2 mv cos theta into this half a v a v, yeah, half a v dv, and sin theta cos theta d theta and a, and we divided by the area a, so a cancel, right? So this is your dp. So now we integrate over the theta and phi. So theta is 0 to pi to, sorry, cos theta cos square theta sin theta d theta, and 0 to infinity, what is the velocity range, 0 to infinity, there is a v, here is a v, so v square f of v dv, and other factor is 2m by 2n, right? So 2 cancel, this is m into n, so n is the number density, n is the, yeah, so here is the m is the molecular mass, right? So 1 molecules, so molecular mass, not a molar mass, molecular mass. So then we get thing, okay, so this is actually gives 1 by third. So you calculates this thing, you get the 1 by third, it is easy to calculate, and we know this, right? So this is a p squared average. F of v is the Maxwell-Boltzmann distributions because we are considering free particles. So and this is a p square average, right? So then we get 1/3 p m n m times n into p square average. right? So any questions up to this point? Yeah, so now we are considering, let's say, so this is actually in general true. Okay, so AV is any kind of distributions. Okay, AV is any kind of distributions, and this is a v square average. Okay, with respect to these distributions, because we are considering that the 0 to infinity AV dv equals to 1, the properly normalizing. Okay, and this is v square generality without any loss of generality, right? So now we consider Maxwell-Boltzmann distributions. Let's say f of v is a v square a to the power minus alpha v square, where a and alpha are constant. I think you know that what is the constants are. So and we know that the v square average for this case, for let's say for MB case, Maxwell-Boltzmann case, for kinetic theory of gases, the Maxwell-Boltzmann distribution. Okay, so what is the v square average? Hello. For Maxwell-Boltzmann distributions, what is the v square average? No, I am talking about the v square average, not v average. Uh, okay, so what is the values of v RMS? Is root of 3 kBT by m, right? So the definitions of v RMS is, okay, so it is easy to calculate that v square average actually 3 kBT by m, right? So how to know that this thing? Okay, so go into that. Okay, so this is simple derive. Okay, so let's say okay, so what is the energy for the molecules for a particular molecules? What is the energy? Kinetic. So air is the only kinetic energy because there is no potential. 3 by 2 kBT, that is from comes from the equiperson's theorem, right? So which is equals to half m v square, right? So this is equiperson's energy, so that means the average energy, right? So equiperson's energy tells that the average energy is 3 by 2 kBT, right? So this is not a average energy is 3 by 2 kBT. Now your case that half m v square, that average is 3 by 2 kBT. Right? So then v square average is 3 kBT by m, right? So it is correct. So from equiperson's theorem, so we have to know to calculate explicitly. Okay, if you calculate explicitly, you get the same results. Okay, so then we just put into this formula what is the pressure for this Maxwell-Boltzmann distributions or kinetic theory of gases. So it's 1/3 mn, and v square average is 3 kBT by m, right? So m cancel. What is this n? It's a number density, right? So n, the total number of molecules by total volume v. So if we put them 1/3, so 3 cancel. So if we put, then this is get we get n kBT by v. So that is our ideal gas equation. PV actually n kBT. Right? So this is your ideal gas equation. Okay. Yeah, any questions? Hello. It is now understood, right? So how do I get the ideal case equations from this distributions? Okay. So next, okay. So now we are solving one and two problems, and then go to the next part. Okay. So yeah. Okay. So now we are calculating the molecular flux. Okay. So then I am going to the one problems. Okay. So first we define the what is the molecular flux. Okay. So molecular flux. Okay. Okay. So I think discuss. Okay, so before I go into this, okay, so I want to discuss some things. Okay, okay, so let's consider a mixture of various gases in thermal equilibrium. Okay, so let's consider mixture of gases in thermal equilibrium. Okay, so then the total pressure. So there is a gas mixer. Let's say three kind of gases mixes. Okay, or in general. So total pressure P is must be follow in cavity, right? So total pressure is additive, or so is pressure. Let's say the we are mixing the three types of gases. Okay, so there is a three partition and open up the partitions. Okay, and let's say P1, P2, P3, right? And after a certain time we mixing them by removing the partitions. Okay, so then what is the total pressure? So it's P1 plus P2 plus P3. How do I know? So follow from this equation, right? So density N is actually simply add up Ni, right? So this means N1 plus N2 plus N3. So they are in thermal equilibrium. That means all are in temperature T, right? So density are equal. So that means the pressure is just sum up. Okay. So that is just the Dalton's law. Okay. So he wants to calculate the partial pressure. Okay, it's P1. It's N1 cavity. Right. So pressure is just add ups. Okay. If the mixture of gases is in thermal equilibrium, then the Dalton's law tells that the pressure is just add up. Okay. So from these equations, okay, PV equals to N cavity or P equals to N cavity. So N is the number density. N is the number density from this equation. Density, right? So there is a two important formula. One is P actually N cavity, and one is this P actually 1/3 mn v square average. Okay, so this is true for any kind of distributions. Okay, f of v. So this is true for any general f of v kind of distributions. Okay, so for particular Maxwell-Boltzmann distributions, you have calculate the pressure, we get a ideal gas law. But if you calculate more complicated system, okay, so if you get a different results. So this pressure actually in general true. Okay. So now we are calculating the flux. I'm going to the effusion process. Okay, by calculating the molecular flux. So molecular flux. Okay, so what is the flux? Okay, so flux is the number of molecules strike per unit area of the wall, right? So the definitions of the flux is the number of molecules, okay, number of molecules strike per unit area, into unit time. So at unit area, at unit time, okay, how much number of particles strike to the walls is called the flux. We define the flux. Okay, it's the molecular flux, the number of molecules strike to the unit area per unit time. Okay, yeah. So then you know that from this previous calculations that the number of molecules hitting a wall at area A is v to v plus dv with velocity range and theta to theta plus d theta this. So in this case the unit area A and unit time dt. Okay, where is the dt? Yeah, so unit time dt. Okay, so this is actually the unit time. That's why you take dt equals 1. So yeah, so then we can use the same formula. So then the flux phi, okay, so 0 to infinity dv 0 to pi by 2 theta v cos theta in f of v dv half sin theta. Yeah, so per unit area, per unit time, there is no area and no a and no dt. Okay, and we are indicating about the all possible values of theta and v, right? Okay, so the possible values of theta is 0 to pi by 2, right? From here we have to see that this is theta, right? So from these portions particle strike to perpendicularly or this, right? So the possible angle is 0 to pi by 2. So theta, the range of theta is 0 to pi by 2, right? So if they hit to the perpendicular or the parallels, okay, so the range of theta is 0 to pi by 2, any directions they can hit. So we are actually the finally projecting the perpendicular, right? So that's why the v cos theta there. So then we can integrate this theta actually 0 to pi by 2 and with the projection v cos theta. So we get so after this kind of integrations, okay, theta and v, okay, for fv, so it's 1 by 4 in 0 to infinity v fv dv. So what is this quantity? V square average. Why v square average? I think there is a v only. Yeah, so 1/4 n v average, right? So this is a flux, right? Yeah. So then for in the Maxwell Boltzmann case, Maxwell Boltzmann distribution case, or ideal gas, that means the ideal gas case, you know that the v average is 8 kBt by pi m, and you know that the flux phi is 1 by 4 in and these things, okay, 8 kBt by pi m. If we replace pressure P actually n kBt, okay, and this implies that n actually P by kBt. So once we replace this, we get a P by root of 2 pi m kBt. 1 second, yeah, 416, yeah, so 2 pi m kBt. So that means the flux is proportional to P by root T, right? Flux is proportional to P by root T, and also the flux is proportional to 1 over root m, the mass of the molecules, and other things are constant. Pi, kb are constants. So flux is proportional to P over root T, and 1 over root m, right? So then there is a problem in the assignment 3. I think you know that the assignment 3 is the problems. Yeah, so consider a container, okay, divided by a partition. Let's say container, okay, and divided by a partition, okay, with a small hole. Let's say there is a small hole and this container, and this whole diameter, actually the diameter is d. Okay, so this small hole with diameter d, right, and containing the same gas each side. Okay, so the gas left hand side is temperature, let's say T1, and pressure P1, temperature T2, pressure P2, right hand side, and the gas same types of gas. Okay, so then if d is much smaller than the mean free path, okay, so there is two conditions. One is that d is very greater than equals to lambda. This is the diameter of this hole, the small hole with diameter d, and another case, this is case 1, this is case 2, d is very greater than equals to, very less than equals to lambda. Okay, so then what is the conditions for this? Okay, so d is very, then what happens? And so if d is very greater than equals to lambda, then what happens? Okay, and it is very less than equals to lambda, then what happens? Okay, and how to get the equilibriums? So this lambda actually the mean free path, mean free path, this lambda. Okay, so and okay, so these portions actually, so this is the flux is inversely proportional to the square root of m. This is actually the Graham's law. Okay? Graham's law. So in this case, okay, so now let's consider, first discuss the second case. D is very less than equals to lambda. So how to get equilibrium for this case? So calculating the flux, right? So from this case, what is the flux here, right? And for this case, what is the flux? So equilibrium get when the flux is balanced, right? Or the same thing. Okay. So both sides of flux are equals, then we get a equilibrium. If there is a small hole and d is very less than equals to lambda, then we need to balance fluxes to get a equilibrium, right? So it's the flux balance to get a equilibrium situation, right? So therefore we know that the flux is p over root t, right? So if you compare the flux and get a conditions, okay, for the equilibrium. So if we just balance calculate the flux the left hand side and calculate the flux in the right hand side using this formula, okay, using this formula, okay, and we equal the fluxes and we get a conditions for the equilibrium situation, right? Any question? So now I am going to discuss that why this d is very less than equals to lambda, we need to have flux balance, and what is the other conditions, okay, leads to. Yeah, so till now any question? Okay, yeah, so so in order to understand this, that what is the mean that d is very less than equals to lambda, we need to get a flux balance, and what is the so we first understand the mean free path. What is the lambda? Okay, so mean free path. Yeah. So what is the mean free path? Yeah, so can you tell me just two lines? What is the mean free path? Yeah, this is true. So okay, so let's calculate. This is sort of kind of things. So okay. So in the previous class, I am talking about that. Let's say calculate at room temperature at, let's say, T equals to 300 Kelvin, and the RMS velocity. Okay, or average velocity. So RMS velocity of into gas, right? Okay. So PRMS 3 kbdy. So calculate this thing, RMS velocity of into gas. So I am already saying in the previous class. Okay, let's recall our going to this. Okay, so which points? Yeah, so there are some points. I'm dealing this thing. Yeah, so in this case, the calculate the RMS speeds of the N2 molecule at room temperature. So you get a 500 meter per seconds, right? So if you use m into 28 gram, you get a 500 meter per seconds. Okay, so then this actually 500 meter per seconds, right? Yeah. So that means the the process like the diffusions. Okay, so one gas diffuse into the another, it's almost instantaneous because this the speed is very high, right? So it is high chance there are two collides. The two molecules, two Nt molecules, two N2 molecules are collides, right? So if the gas is diffused to another gas, okay, before the collisions, okay, it's like an instantaneous process. So diffusions is sort of kind of an instantaneous process, okay, because they are very, the speed is around the 500 meter per seconds, okay. So two N2 molecules it collides too quickly, okay. So in order to get a diffusion process like that, the one gas molecules diffuse into the other gas molecules, okay, so it is before the collisions, so it's like an instantaneous process, okay. So then in order to understand the mean free path, first to understand the what is the mean collisions time, okay, and what is the cross sections of these collisions, this kind of things. Okay, so recall our the mean collisions time. So if you know that the mean collisions time is tau actually 1 over n sigma v, right? So sigma is the collision cross section, okay. So what is the mean collisions time? This is the mean collision time, okay. So this is the time, okay, which elapsed between the collisions, the average time elapsed by the particle between the collisions, okay. So the average which is the average time elapsed between the collision, okay. So average time elapsed between the collisions, okay. So between the two collisions, this is the average time elapsed by the particle, okay. and we are considering that the other particle, other all the particles are frozen, only one particles hit to the other particles, okay, that is at rest, and we are calculating that the average time between the collisions of these particles are this 1 over n sigma v, where v is the average velocity, okay, the average velocity of this molecule, okay. So where is the sigma is the collision cross section, okay, of molecule. So this is the collision cross section of molecule. What does this means? Okay. Of molecules, okay. So which is something like a cross sectional area, okay, of the given molecule, okay. So that means, yeah, so which is something like the cross sectional area of the given molecules, okay. So what is the cross section area? So here is that so we are interested in the short range interactions. That means let's say if a molecule this the molecule is like a billiard ball, okay, and the hard sphere, this is the assumptions, okay, because we are interested at moderate temperatures, so around room temperatures, so we can consider the molecules as a billiard balls, and there is some finite radius, okay, let's say a1, okay, and if we collide the other molecules, okay, the same radius, with all our molecules are identical, let's say, so this is again the radius is a1, okay, so is the total is 2a1. So we are considering a 2a1, this is a big region, okay, so this region we are considering that within this tube, okay, with the diameter is 4a1, okay, double of this, okay. So is the diameter is 4a1. So this is a sort of kind of assumptions, okay. So we are interested in this short region around the two particle collisions region, okay. So within this tube, if the particles come, they collide, okay, because they are random collisions, so each molecules collide with any other molecules, okay, but we are consider only that those are collides, yeah, so those molecules are collides are in this region, okay. So in this 4a1 types of cylinder, so in this region if the molecules comes, they collides, okay, other molecules are cannot collides, okay, so they collide some other molecule, other particles, okay. So let's say this molecule sorry, yeah, so let's say there is a molecules, okay, there is a molecule, let's say center is there, and here is a molecules, let's say center is there. So we consider the collisions of these two molecules, so not consider these molecules, okay. So you're not considering that this molecule collide with this molecule, because the center is actually outside of this region, okay. So you're only considering this molecule collides, this molecule not collide, this molecule collide some other molecules, let's say these, okay, because they are region again the 4a region, so there is a 4a1, but this not collide, okay. So this thing not collide, okay, this molecule collide, okay, this collision cannot happen, okay. So in this region there is another tube, they collide that. So in this way we are calculating the things, okay. So this is the collision cross sections, okay. So that's the region we are interested, that is called the collision cross sections. So this is actually pi times 2a1 the whole square, right? So that is called the diameter of the molecule, because this is a1 radius, diameter is 2a1, and all the molecules are identical, so all the molecules of diameter is d, so pi d square. Yeah, so it is understood. what is the collision cross sections, why this is pi d square. Okay, so now, yeah, so still we are at moderate temperatures. Okay, and the molecules are hard sphere. Okay, so they are just like a billiard ball. So now we calculate the mean free path. So mean free path, the crudely speaking, that the length, okay, between the two collisions. Okay, so the travel a distance between the two collisions, that is called the mean free path. So if you know the collisions time and multiply it by the velocity, right, we get a mean free path. So mean free path lambda, yeah, so mean free path lambda is just a p average times mean collisions time. So the collision time is the average time between the two particle collides. Okay, and the mean for the average distance traveled. Okay, it's the multiplied with the velocity, p average. So what is this p average? So again we are so again we are, that's this v average, that means, yeah, so again we are considering that the only one molecules are moves, other molecules are frozen, but this is not the case, right? So all the molecules are moving, so that means this v is not a v average, is actually the relative velocity. So let's say this molecule and this molecule collides. Okay, so the molecule, the speed of this molecule is v1 at the velocity, and this is the v2, let's say, in this directions. Okay, the velocity vector, any directions they can have move. Okay, so if they collides, that means this v average actually the relative velocity. Okay, v average actually the v1 average minus v2 average, right? So if we consider the other molecules, let's say v2 at rest, then v2 goes to 0, right, and v1 is just v average, but this is not the case. So all the molecules are moving, so the v average is actually the velocity vector, actually the relative velocity. So in this case the relative velocity, so relative velocity actually v1 minus v2. Now we calculate the vr square, this v1 square, v2 square minus 2 v1 dot v2. So now we calculating the average of this vr square, that means the average of v1 square, average of v2 square minus 2 average of v1 dot v2. So what is the average of v1 dot v2? Yeah, so the average of v1 dot v2 is actually gives that okay, so this is actually in the mod of v1 mod of v2 into cos theta. So average means that the integrate about the all possibilities of theta. So if we integrate that 0 to 2 pi cos theta d theta, you get a 0, right? So that means this is actually 0. So then that the vr square actually v1 square average and v2 square average. Now you know that the each molecules are velocities are independent to each others, right? So v1 are independent to v2, so we can calculate the for Maxwell Boltzmann distributions. So this is actually 2 v square average, right? Both are same, so it's clear. Yeah, so both are same. Then so here we have also making assumptions that this vr average is sort of root over vr square average. So this is assumptions. Assumption is that this is correct up to some certain order. Okay, but so still it is valid. Okay, so vr, we can say that the vr average and roughly the root over v square that average. Okay, but this is not true actually, but we can say that it's approximations to this thing. Okay, this condition. Yeah, so in his okay, so that thing, so what is the vrms square? It actually v r square average minus v square average, right? So if you consider that the v square average, sorry, v square average and equals to v square, v average the square, then vrms is 0, right? That is not the case, right? The RMS velocity is not 0 always. So this is a approximation that if you calculate VR square average and then root, we get that VR. Okay. So like a standard deviations, okay, the standard deviation is not 0 always. So the v square average and v average both are not same. So that's why we have get a difference. Okay, so we approximate these things and we get this thing actually root 2 v square average. Now put into this formula lambda. So lambda is root 2 v square average into tau 1 over n sigma v. Right? So this is a v average and this is a v square average. So yeah, so then what is the sigma is pi d square. So if we calculate what things we calculate, yeah, if we calculate the lambda, so this is actually this is approximation, so it's approximately 1 over root 2 n sigma. So we know that the v square average is 3 kBt by m and v average 8 kBt by pi m the square root, right? Sorry, this is not a v square average. This is root 2 v average. Yeah, so root 2 v average. This is not a v square average because vr square average root 2 v square average. Now we again take an assumption that the v square average actually v average the square. Okay, so that's why the root 2 v average. So this is sort of kind of approximation. So VR square average is 2 v square average. So 2 is root 2 and then square root of v square average. This is again this kind of assumptions. Okay, so it's v square average is approximately v average, right? So this is assumptions that you can do the same thing. So backwards you can use this. You can get this. So this is actually root 2 v average. So this v and this is actually v average. So v average and v average is cancelled. So you get a root 2 n sigma. And in terms of that, so 1 over root 2 n pi d square. So this is your mean formula with the Maxwell second order corrections, right? With the Maxwell corrections that both our molecules are moving. So zeroth order, that means the all molecules are frozen. So this root 2 factor is not there. So now we correct first order, second order, okay, the Maxwell corrections, etc. So we get these types of formula. So here we say that intuitively we can say that this is the right. We can get this thing up to certain order approximations. Yeah, it is now clear. Yeah, so then yeah, so once you know that the lambda, this formula, okay, so you can calculate various things. Suppose let's say given the number density n, okay, okay, so let's do one problem. Okay, exercise 1. So calculate the mean free path for a n2 gas again. Okay, so we calculate the RMS velocities of n2 gas. Okay, so let's say calculate the mean free path. So calculate mean free path for a gas of N2 at T equals to 300 Kelvin, right? And let's say the diameter of this N2 molecule is 0.37 nanometer. How to calculate? So the diameter is given, right? Okay, but there is too many formula, but we only know this formula, right? So lambda is 1 over root 2 n pi d square. So we know d, right? The d is given, right? So d is known, right? This 0.37 nanometer. Pi is constant, root 2 is constant, only unknown is n, right? So how to know the n, right? So again, I'm calculating at room temperature, right? At room temperatures. So what is the pressure at room temperatures? The standard isotopy, ISTP case, okay? So pressure is P actually n kVt, right? So if you know T, if you know P at room temperatures, okay, and the kV is constant, you calculate n from this equation. So it's P by kV T. What is the pressure at room temperature? Unit? Yeah, so that's 1 atm, right? So it's pressure at room temperature is around 1 atm. That means 10 to the power 5 Pascal. So there is a factor 1.055, but the order is 10 to the power 5 Pascal. Okay. So we calculate this 10 to the power 5 and T is 300 Kelvin and 1.38. Sorry. Yeah, so 1.38 into 10 to the power minus 23. So we calculate, we get a n, right? And it's the order of 10 to the power 25 per meter cube. Okay. So once you know the n, right, we calculate the lambda, because everything is known. D is known, n is known, pi is known. We calculate the lambda. Okay. Just 1-2 minutes to calculate and we get the results. Okay. So that means if you calculate and we get the lambda, okay, so this is actually 6.8 into 10 to the power minus 8 meter. Okay, so now we try to understand that the RMS speed is actually the 500 meter per second, and the mean free path is 10 to the power minus 8 meter. Okay, so it's two small time length they have collides. Okay, so the diffusion like process is the instantaneous process, because if they diffuse to other gas before the collisions, okay, so it's like instantaneous. Okay, so too much less this mean free path. Okay, so it's too small. Okay, and speed is too high, so it's a quickly collides. So if you want a diffusion like process, so it's an instantaneous type process. Okay, so then okay, so let's go 1 and 2 3 problems in the assignments. Yeah, so mean free path. Okay, so now we discuss the diffusions like process. Okay, so I think week 2 assignment solutions is given, right? So if any problem, yeah, so any questions from the solutions, so you get a different answer, or the answer is given in the another option. I think there is only one formula. This is lambda actually root 2 n pi d square. So the other quantities are given, we have to calculate the mean free path. So there is a nothing too difficult here. Okay, so we are going to the diffusions kind of things. Yeah, so now we are discussing the things that we are left. Okay, so what is that means that is d very very less than equals to lambda and d very very greater than equals to lambda. Yeah, so these things. Yeah, so when this diameter of the hole is very very less than equals to lambda, right? So that means there is a kind of effusion process. Okay, so if this d very very less than equals to lambda, there is a kind of effusion process, and if d very very greater than equals to lambda, okay, so if d is very very greater than equals to lambda, right, so there is a kind of effusion process. Okay, so let's check this thing. Yeah, so we are this is actually the effusion region, so we are in the effusion region. Effusion region, and if d is very very greater than equals to lambda, then there is a diffusion region. Right, so in this case, if you reach equilibrium by balancing the flux, balance the fluxes, because there is a effusion process. Okay, so we need to calculate that what flux actually how much number of particles strike to this wall, okay, to this hole, because this hole is now too small. Okay, so there is a probability. Okay, so we have to calculate that the how much number of particles actually uh, hitting to this hole, okay, or to the wall, what the hole is actually. So then this is actually the effusion region. So we can balancing the fluxes. Okay, so that is the definitions of the flux. Now if d is very very less than equals to lambda, so there is a big hole types of thing, so it's a diffusion region. That means just you know that the thermal equilibrium there is a temperature is fixed, so we are only fix the pressure, so p1 actually p2, just like a mixing of two gas. Okay, so there is a two compartment container, okay, and divided by a wall, and suddenly they remove the walls or there is a big hole type of thing. So just the two gas are mixing, okay, without any sticking to the walls kind of thing. So the gas are easily mixing, okay, because they are the diameter of this hole is much much larger than the mean free path. Okay, so before they are the collisions of these two particles, they can go another side and they mix with the other particles in this side. Okay, so if this hole is very very greater than equals to lambda, that means this part molecule collide with these molecules. So in these collisions, so they can reach to this before so instead of this they collide with this molecule, they can go through this hole and mixes with the other particles. Okay, and this is a kind of gas mixer. Okay, and this is a diffusion region. So on the diffuse with the one side particles to the other side. Okay, and we reach equilibrium by uh, equate the pressure of the both side. Okay, so this is the balancing the pressure, balancing the pressure. Okay, so if it's d very very less than equals to 1. Yeah, so any question? It is understood, right? Okay, so what is the difference between the two conditions? One is the effusion and is the diffusion. So now we are going to the transport property of gas. Okay, so what is the diffusions kind of thing? So that is related to the transport property of gas. Okay, so how much time we left? Yeah, so almost 30 minutes. Okay, so we are going to into the formula. Okay, so that is needed to solve the assignment, and then we solve the assignment in the last 15 minutes. Okay, so so we are going to quickly from this formula. So okay, yeah. So far we discussed the dynamics of a gas in equilibrium, right? So far we discuss the dynamics of gas. Okay, that the kinematics of the gases. Okay, dynamics of gases in equilibrium. That means there is a fixed number of molecules, okay, at a constant temperature and pressure. Okay, there is a number of molecules fixed. Okay, so now we are considering that the diffusion kind of process, the number of molecule exchange. Okay, so the transport property. Okay, so they can transport the, so which kind of transport gives a different things. Okay, different quantities. So yeah, so we consider a, but so this is equilibrium. So far we discussed the dynamics of the gases in equilibrium, and now we consider the non-equilibrium cases. Okay, so where they can changes. Okay, so in general in the thermal physics or in the thermodynamics, so there is a system that is we are interested in. So this is a system, because in that systems we are interested in, and outside of these systems, so these are the surrounding. Okay, and so this is a system. Yeah, so this is a system, this is a surrounding. So this is surrounding, the outside of this system is a surroundings, and the system plus surrounding, this is the whole part, is a universe. Okay, so we are only interested in the system. Okay, and we are allowing that the number of particles go through this system to the surroundings, but the universe is the number of particles is fixed. Okay, but so we are only interested in the system. So the changing in the number of particles in the system, that means we are saying that the non-equilibrium type of things. Okay, they are not in equilibrium, but in the universe it's a different things. Okay, so we are system plus surrounding is constant. Okay, so number of particles is going through the system to surrounding, or surrounding to system, but the universe is constant, right, in the universe. So that's why the, so different kind of transport, and we gives a different kind of quantities. Let's say it's called the viscosity. So this is actually gives a transport of momenta. Okay, transport of momenta. Dui, it's called the thermal conductivity. It gives the transport of heat or energy. So heat is a flow of energy, right? So it's a transport of heat. So heat is a transport from system to surrounding. Transport of momenta, system to surrounding. Okay. And third is called the diffusion. This is actually the transport of particle. Transport of particle. Okay, or molecules, whatever you say. Yeah, so for a so if you know that the how to calculate the viscosity for a fluid like system or a gas like system, similar kind of things. So there is a uniform flow, and so there is a uniform flow. Okay, and they can reduce between the two slabs. Okay, so if slabs are going into the different directions, so there is a gradient kind of things. Okay, so there is a gradient kind of things. Okay, so the shear stress between the layers of the layers. Okay, so this is a one layer and this is a one layer, they are moving in opposite directions. Okay, and inside there is a gas or fluid. Okay, so gas or fluid, so there is a velocity gradient. Okay, so and this gradient, actually the coefficient of this velocity gradient is the viscosity. Okay, so let's write in the things. Okay, so the shear stress between the layers is proportional to the velocity gradient in the direction. Is proportional to the, sorry, yeah, is proportional to the velocity gradient in the direction, velocity gradient in the direction perpendicular to this. So these directions there is a velocity gradient, so perpendicular to this layer. Okay, so perpendicular to these layers. Okay, and the proportionality constant is called the coefficient of viscosity. So proportionality constant is called the coefficient of viscosity. Okay, so this is actually eta. So I think you know the formulas are derived in the class, that 1/3, even I am not going to the derivations, it's lambda and this is v average. What is a lambda? Is the mean free path, right? So okay, so this is the coefficient of the viscosity. So now the important things now, that what can conclude from this. Okay, so what is the lambda? So lambda is previously derived that 1 over root 2 n pi d square, right? So then that eta is 1/3 m times v average pi d square and some other factor pi root 2 etc. So this is m, actually the molecular mass, so n is actually cancelled. Okay, so there is a n, there is a n is actually cancelled, right? So what is imply for, what is the implications for this, the cancellations of n? So how to calculate n in the previous case, in the previous examples? It's calculated n from the pressure, right? So here is the independent of the n, means that the diffusion process, the coefficient of the diffusion is independent of pressure, right? Independent of pressure, this is the important things. So the n actually the independent of the pressure, right? Because there is n actually, so we look into the trace to the n. Okay, so what the n actually comes. Okay, if there is a no n, there is a no pressure, right? So there's the viscosity, the coefficient of the viscosity actually the independent of the pressure, they proportional to the mass, inversely proportional to the 1 over t square. Okay, so this is the independent of the pressure. Okay, so now you might be asked that so if you increase the pressure, right, so you should better is the transmitting the momentum, because you have a more molecules to do with it. So what is the increase in the pressure? So if you, let's say if we increase the number density, n is increased, this implies that pressure is also increased, right? So that means there is a more molecules you have. Okay, so there is a more molecules to do with the diffusion process, one particular one portions to another, right? So there's some kind of contradictory result, right? So it is clear that the question what I am talking about, that if we increase the m, the pressure is increases, that means there is a more molecules, right, in the container, and the diffusion kind of process it should be increasing, right? sorry, diffusion is a viscosity. I'm sorry. Yeah, so viscosity. So viscosity means that the transferring of the momentum, right? So the viscosity, okay, so the viscosity is the better to have the transmitting the momentum from one place to another, because you have a more molecules, okay. So this actually cancel by the uh, again, so why the n is cancelled with this thing? So n is cancelled actually the mean free path, okay. So if we increase the n, right, so there is a more possibility to transmitting the momentum from one place to another, but inversely the lambda is actually cancelling this effect. So lambda actually reduce this transmitting the momentum from one place to another in such a way that they can actually cancel, okay. So mathematically this in cancellations, and the if you gives the argument, then you can, in this way you can tell, okay. So if you increasing n, okay, so in this case that eta is actually 1/3 m in lambda. So if you increase the m, if you increase the pressure, that means you it's a more possibility to transmitting the momentum one place to another. But in the similar way, the lambda is actually the opposite, okay. So it's less effective from the transmitting the momentum to one place to another, so they are actually cancelling, okay. So the mathematically we can say that this n and this n is actually cancelled, okay. So then we go through into this, okay. So now we, okay, so now we are going to the problems, okay. So then eta, okay, so eta actually proportional to v average, right? Another thing is d and pi or m are things, so we are only interested in v average. So this is v average is proportional to root t, right? So v average actually root over of 8 kBt by pi m. So we are only interested in temperature. So eta is proportional to square root of t, right? And inversely proportional to 1 over d square. Okay, actually let's say m over d square. So these are two important things, okay. So it's the diameter of the molecule and the mass of the molecule, okay, proportional to the mass of the molecule, okay. So inversely square to the diameter of the molecule, and the temperature is, the viscosity is proportional to root t, okay. So then going to the assignment problems, okay. So assignment 3, right? Yeah, so suppose you given that the coefficient of the viscosity, okay, at suppose you know that the viscosity of the coefficient, or let's say calculate the viscosity of the coefficient for, let's say, n2 gas. So for n2 gas, okay, let's say at room temperature T is 300 Kelvin, okay, and 1 atm pressure, right? So you know that the atomic weight of this m, what is this m for n2 gas? No, this is m, right? It's not a molar mass. 28 gram. This is a molecule. No, this is a 20, this is a molecular mass, right? It's not a molar mass. 20 is correct, but it's not gram, right? So recall the previous class, okay, what I'm talking about, that why this gram actually comes into the picture, right? So you say that clear that the gram actually 1 mole of C, it's not a 1. So if multiplied by Na number of molecules gives a gram, okay, but we are talking about 1 molecule. It is understood? Yeah. So it's the atomic unit, right? So you are only considering 1 molecules, not the any number of molecules, 1 mole of molecules, okay. So it's 28 u. So now you know that 1 u actually 1 over na gram. So converted this and we calculate. Okay, so now with the diameter I'm already given that in the previous exercise. The diameter is actually 0.37 nanometer. 0.37 nanometer, right? So if you calculate the V average, okay, and you just put that eta is 1/3 m in lambda V average. So if you know n, right, if you know lambda, okay, or just put in this formula 1/3 m V average √2 pi d square. So once you calculate V average using the formula √8 kVd by pi m, you know m, this is m. So converted this atomic unit to gram 1 over na, and this na actually, if you know the Avogadro number, 6.023 into 10 to the power 23. So you calculate the viscosity, right? Because everything is known, m known, V average known, d known. You calculate, right? Hello. Yeah. So now suppose the another thing, suppose we given that the, let's say, density. So let's consider a again N2 molecule. Okay, again we consider N2 molecules. Okay, and so given the density of this molecule, let's say given the density, let's say, okay, so it's roughly around some 0. Let's say what can I say? Okay, so 0 2 3 kind of things. Okay, so it's kg per meter. So number is not just taking an arbitrary number. Okay, so given the density this, okay, and let's say the coefficient of the viscosity is once you calculate this and we take this value, okay, here. So let's now for a moment we take the arbitrary values. Okay, so let's say given some 83 times 10 to the power minus 5 Newton per second per meter square. Okay, so the unit is actually Newton second meter square. Okay, so that is the unit of this coefficient of the viscosity. So this eta is given, the density is given, okay, and let's say V average is also given, let's say 500 nanometer per second, sorry, 500 meter per second. Okay, so calculate the lambda. How to calculate? So in this formula put that things, eta actually 1/3 m in lambda V average. So V average is given, right? So V average is given, eta is given, right? Lambda is given. Just okay, so we want to calculate lambda, right? So this is we calculate. So now the density is given. Okay, so what is the density? Okay, so it is crucial that we are here we are talking about the density, not a number density. Okay, so this is not n, right? So how to get the density from this? Okay, so what is the definition of the density? This, right? The total mass by total volume, right? So what is the total mass? N into m. So there is a one molecule have mass n and there is n molecules are there, so total mass n into m, right? Hello. Yeah, so then we divided by v. Now you know that n by v, your small n and m, right? So rho actually n times m. So this is the number density n by v into m, you gives a rho, the density. So if you put these things, so that means you know mn, right? Because you know rho, so this is actually rho. So you know rho, and you, that means you know n times m. So one thing so you have calculated is lambda. So you get a lambda actually 3 eta by rho v average. Just putting the data into this right hand side, you get a lambda, right? Okay. Yeah, so now we are going briefly about the thermal conductivity and the diffusion coefficients. Okay. Yeah, so now we're going to first. Yeah, so thermal conductivity. Okay. Yeah. Okay, so all of these thing calculations are at moderate temperatures. Okay, so if this temperature is too high and too low, okay, so then there is the other factor comes into the picture. Okay, so if the temperature is too low, then we are going to quantum corrections. Okay, we need to quantum corrections. Okay, and if this temperature is too high, then they can some other types of problem comes into the pictures. Okay, so all the derivations are here calculating at moderate temperatures. Okay, it's kind of room temperatures. Okay, not too high, not too low. Okay, so this thing that the viscosity is independent of the pressure and the proportional to t to the power half square root t to the power half. Okay, so these things are all at moderate temperature. So that is things I want to say. And okay, so now we are going to the thermal conductivity. Thermal conductivity. So thermal conductivity means the transfer of heat, right? So it is transport of heat, right? So how much amount of heat flow along a temperature gradient? Okay. So what is the thermal conductivity? Namely, say that the how much amount of heat flows along a temperature gradient. Along a temperature gradient. Okay. So which is actually depends on the thermal conductivity of the material, right? Which depends on the thermal conductivity of the material, right? Of the materials. So that is where the thermal conductivity is defined. Okay, so the you get that the J is the heat flux, okay, in 3 dimensions. Heat flux, okay, in 3 dimension. Okay, so this J heat flux is actually minus kappa times the gradient of T. Okay, it's a temperature gradient. Okay, so this is actually the temperature gradient, and this is your thermal conductivity. Yeah, so this minus sign actually if we this is the opposite. Okay, so the amount of heat flow with opposite to the temperature gradient, that's why there is a minus sign, because the vector quantity. Okay, So J is opposite to gradient of delta T, it keeps a minus sign. Okay, so that's the significance of this minus sign. And if you calculate this K, okay, this is actually 1/3 CV lambda V average is kappa. Okay, so I'm not going to the derivations. Okay, so this kappa 1/3 CV lambda V average. Okay, so again think that what is CV? CV is that the C molecule, okay, so A times C molecule. So this is a heat capacity of a single molecule, and this is the total heat capacity per unit volume, right? So okay, how to get this thing? This is a N times C mole per B. So this is a heat capacity of a single molecule, not in unit volume, because we are considering single molecule. There is no need to consider the volume. Okay, so heat capacity of single molecule. Okay, and now there is a N molecule, so multiplied by N, so total heat capacity. Now we divided by V, that means this CV, the heat capacity per unit volume of a total system. So heat capacity per unit volume. Okay, so try to understand this thing. Okay, so it is clear now, right? So what is Cp, what is C mole? Okay, how do they relate? Okay, so now we are using this formula. We try to solve the assignment problems. Okay, so let's say the thermal conductivity. Okay, so the thermal conductivity then again proportional to, okay, so lambda is what is the lambda? Lambda is 1/3 n, sorry, 1 over root 2 n pi t square, right? And Cv is proportional to n, right? N C mole. So we say that the kappa 1/3 n C mole into lambda is 1 over n root 2 pi d square and V average. So again n cancel. So again this is independent of pressure. Okay, so thermal conductivity again the independent of the pressure, and the similar way as in, we discussed in the before. Okay, in the in the viscosity case, right? But again the kappa similarly the proportional to root V, that means is proportional to square root of t, right? Other things are constant. Okay, the heat capacity of a single molecule is constant, C mole is constant, so the kappa is proportional to square root of t. So now we say that let's say the thermal conductivity of a gas at temperature T. So let's say at T1 thermal conductivity is K1, at T2 thermal conductivity is K2. Now we just relation that the, let's say K2. Okay, so now we let's say given T1 actually, let's say 42, and calculate K2 by K1. Okay, so how to calculate? Just divided that. Okay, so K1 by K2 is the square is actually T1 by T2. So okay, so this T1 actually 42, so this is 4, so that means K1 square is 4 K2 square, right? So that means the K2 by K1 you calculate that, K2 by K1 actually half. Okay, so these types of things that you know that the how this thermal conductivity relate with the temperature, and how it relate to the diameter of this molecule. Okay, so this again the kappa is proportional to 1 over d square kind of things. Okay, So it changes. Let's say there are D1 types of molecules and thermal conductivity K1, and D2 types of molecules thermal conductivity K2. So if there is a K1 actually 4K2, we calculate D1 and D2, relate them. Okay, so it's an easy way to equate the relations. Okay, so next let's say yeah, now we going to the third case. Yeah, so now let's say the thermal conductivity of a gas ensemble. Now we're going to the third problem. Let's say the thermal conductivity of gas in assembly at a temperature T is K at a given number density N. So write down the thermal conductivity formula. K 1/3 CV lambda V average, 1/3 CV lambda V average. So let's say at temperature T, the thermal conductivity kappa, okay, with number density is N, right? So if the number density increase 3 times, right, let's we contact the number density. If let's say number density N, it goes to, let's say 2N, right? So then kappa goes to, yeah, so can you tell me that what is the kappa changes if number density increase or decrease it 2 times or half times? Then kappa is change or not? Yeah, because this is independent of the N, right, as we discuss. Yeah, so that's a good answer. Good, that is independent of the N. So that if you change N, that is a no change in kappa, right? So now we are calculating the diffusion coefficient. Okay, and then we discuss two problem in the diffusions and in this series. Okay, so the diffusions is the same kind of things. Okay, so the last things we have going to discuss the diffusions. Yeah, so let us go quickly through this thing. Okay, so diffusion. Okay, so I'm not going to the derivations today due to this lack of time. Okay, so just putting the formula, D is 1/3 lambda V average, right? If you calculate the diffusion coefficients, I think sat derived in the class. Okay, so you get this formula, right? So in this case there is a no N, right, in the front of this lambda, right? So that means the lambda is inversely proportional to the N, right? So what is the lambda? Explicitly is 1/n by d square, and there is a √2. So in this case d is inversely proportional to the n, right? So unlike the previous case, okay, n is the number density. Unlike the thermal conductivity and viscosity case. Okay, so the coefficient of the diffusion, okay, so the diffusion constants, okay, it depends on the number density. That means it depends on the pressure, right? So that means it depends on the pressure P. Okay, and it depends on the T to the power. So okay, so T is lambda, so n is depend on the pressure. So so P actually in kVt, then n is P by kVt. So it depends on T, and V average is V average. So we are only interested in the temperature dependence, right? So V average is actually √T, then T to the power 3/2, right? So diffusion coefficient is led to the temperature is to the power 3/2. So now we are going to the problems that suppose you have again the same things. Let's say yeah, so the diffusion coefficient, let's say at temperature T1 the diffusion coefficient is D1, at temperature T2 diffusion coefficient is D2. Now let's say D2 is 8, D1, then we calculate what is T2. by T1, right? So it's calculated, right, easily, just putting that things. Okay, so T2 by T1 actually, T2 by T1 that whole to the power 3 by 2, because the proportionality constant actually cancel. Okay, so then we know that T2 by T1 is 8 and T2 by T1 is 3 by 2, so then 8 is actually 2 cube. Okay, so it's cube cancel, that means T2 by T1 is actually 4. Okay, so this T2 by T1 actually 4. Okay, so we get a 4, and then this T2 actually 4 T1. Okay, so then the another thing, so let's say, okay, so let's consider a container. Okay, and divided by the container, and in this case the pressure is P1, temperature is T1, pressure is P2, temperature is T2, right? So pressure P1 at temperature T1, and in this case pressure P2 at temperature T2. Now we removing this wall, okay, and mixing, allow the mixing of these gases. Okay, so if Pb, P2, let's say 4 times P1, and T2, let's say 8 times T1. Okay, then we calculate the diffusion coefficient d2 by d1, right? So we know how to relate P and how to relate T, right? So D is inversely proportional to the P, and so okay, so just do things, that d2 by d1 is actually, yeah, so d2 by d1 that whole to the power 3 by 2, and inversely proportional to the temperature, so P1 by P2. So if you know T2 T1 and P1 P1, you calculate T2 T1, right? So it gets some T2 sometimes into T1. Just put in the formula. Just put the data in this. So P2 actually 4 P1 and T2 actually 8 T1. So you get this thing. Okay. Let's do it explicitly. Okay. So T2 T1 is 8. So 3 by 2. So it's 2. Yeah, so what is this thing? Yeah, so 64 times 4. Sorry. Yeah. So 64 times 8, the square root, and then it's 4 root. Okay, so in the similar way, if this is this relation is given, how the P2 P1 and T2 T1 relate, and we can calculate T2 T1, or the you can say in the opposite way. Let's say D2 D1 and is given, okay, and then we calculate, let's say P2 P1, okay, and T1 T2 is also given. Okay, so this thing is so this thing, I think the assignment 3 problems is now solved. Okay, so yeah, there is no other questions. Okay, so now there's one more question is left. Let's say there is a 2 isotopes. Okay, so let's say define that's a hydrogen 1H and 2H. Okay, and we are allowing them, they are passed through the barrier. Okay, that means it passing through the system to surrounding. Okay, so then which of this isotope will be present in the larger quantity in the collected gas? So this is actually depends on the diffusion coefficients. Okay, so how do I know that which are going to the larger? Okay, so this actually depends on the So what is the diffusion coefficient is proportional to? Diffusion coefficient D is 1/3 lambda V average, right? So how it depends on the mass? Is inversely square root of right? So V average actually 1 over root m. So if A is increase, or let's say 1 over a molar mass, okay, right? So we can return that this actually 8 RT over pi n. This is a molar mass. So this V average is 1 over root m. So we increase m, that means the V average is decreases and the diffusion coefficient is decreases, so it's less. Okay, so there is a, so 1H1 is the more, 1 is the more, right? So 1H is the larger quantities, okay, in the we have to collect, right? So this is a larger. Okay, so any questions till now? Okay, so I think assignment 3 problem is already solved. Okay, so just go through them, and there are some data is actually changes, so you just changing the data and calculating the same thing, okay, in the same way you get a correct answers. Okay, okay, so you'll see in the next session. Thank you.